Hi, good morning, everyone. So today we will discuss about a priority queue, okay, and maximum entropy. Yeah. So this is the last installment of queuing theory. Okay. So as you remember, candle notation. Okay. Uh, we have A, B, C, D, E, F. Right. That is. So you have A, B, C, and then D, E, F. This is the candle notation. Do you still remember what is A in this case? The candle notation in queuing.
A is arrival rate, arrival rate.
Yes, arrival distribution. Okay, so usually we put M, for example, M1. So the second one, the B, what is this B? BV.
The surface.
Yeah, the service. Okay, and then C is the
Server.
server, the number of server. Okay, this is the number of parallel server. Okay, it's not the number of server, but the number of parallel server. So even if you have a serial, many server, but in series, they are actually one. You need to remember that. Okay, the lack of understanding of what the meaning of server here is the one that caused until today why there are still a lot of queuing. Okay. And these two, we discussed about the number of, what is D in here? Do you still remember last meeting? We discussed about it. D is
Capacity.
capacity. And then E is
Population.
population. Very good. Okay. The last one, F. Okay, we did not discuss about it, right? The last one is actually the queuing discipline, okay? So it is the last one that we will discuss today. That's usually F is given, queuing discipline is always FIFO, right? First in, first out. And in fact, that's what many people think that queuing is about waiting line, okay? So today, we will discuss something else with this we change this F. Okay, so the queuing discipline is not FIFO. Okay, we call this priority queue, and this happening in a lot of cases. Okay, again, if you check in Google priority queue, there are also another name of priority queue, which is a data structure. Okay, so in here is totally different. So we are not discussing data structure, we are discussing about the queuing theory. Okay, so why we need priority queue? Because waiting costs of certain priority customer is actually higher. Okay, so who are they? Probably patient in emergency in hospital. Okay, in the bank they create a priority customer, people who already put their saving much bigger than certain amount of money, okay, and so on. Okay, so in the government probably they put priority to the elderly. So the waiting cost for priority customer, what we call priority customer is up to to us to define what is priority customer. So the assumption is the waiting cost for the priority customer is higher. And the cost here is not necessarily in terms of money. Right? For example, if you put the cost in terms of money for the elderly, that is probably lower because they are not income generating anymore, right? They are pensioner, usually they already retire. So, but in terms of the pain, cost in here, the meaning of cost is generalized cost, can include the pain. Okay? If the elderly waiting too long, they will get higher pain compared to the normal customer. That's why they are considered as a higher priority. Okay. Now this priority queue have two types. One is called preemptive priority queue, and the other one is non-preemptive priority queue. So, what is preemptive priority queue? Okay, the service of the lower priority customer may be interrupted in favor for the arriving customer with higher priority. So, if a new customer arrive, okay, and that customer is higher priority, okay, even if the server still serving the lower priority customer, the service stop. Okay, the service stop and then it interrupt. Okay, interrupt means the service stop and then will attend the higher priority customer. Now, non-preemptive, in the other hand, is when when a customer is in service, okay, then that customer will leave the facility first, okay, after the service is completed, even if the priority customer arrive. So there is no stop in service. So can you think of situation preemptive and non-preemptive? Can you think of a situation? What situation is preemptive priority queue? For example, in the hospital, okay, when emergency patient arrive, okay, very bloody, and the doctor still doing attending other lower priority customer, okay, will the doctor stop attending the lower priority customer and then immediately attend the higher priority customer, right? So in that case, this is preemptive priority queue, right? So, but in the bank, for example, okay, you are lower priority customer, right? And then say the VIP come to the bank. Of course, the teller will still serve you even if you are lower priority customer, okay? Until you are finished, then the next customer is the VIP. So there is no stop in serving you, even if you are a lower priority customer. Okay? In preemptive is different, right? So they need to stop the service immediately. Similarly, inside the computer program, okay, you can set either preemptive or non-preemptive. Okay? For example, a certain task, if you type Control-Alt-Delete, for example, okay? If you press in Windows, Control-Alt-Delete, that is preemptive. Okay? That means whatever you are doing, suddenly it will pop up that windows of the task. So the CPU will of the certain program will be interrupted. Okay? If the higher priority program, for example, Control Alt Delete, is launched by user. So the same thing with medical staff in emergency room will give priority to the life-threatening case first. Okay? So non-preemptive priority rule, they are just the normal priority that we are doing in the bank or even in Disneyland, okay? VIP cases. So our queuing theory formulas today is about non-preemptive. Yeah? It's not about preemptive, it's about non-preemptive. So now I'm asking about, let's discuss something like this, about preemptive rule. Okay? The clerk answered the phone when the customer in front of her has to wait. Okay? And she preemptively give higher priority to the random caller, isn't it? So now, or even you, for example, you answer the phone in the middle of conversation with someone else. Okay? That means actually you are giving preemptive rule to the higher priority to the caller of the person you are compared to the person that you are conversed to, right? So that question is, what do you think to the person in front of you will feel? So the question again is, does it ethical to do a preemptive priority? And what you're supposed to do? Say you are in the meeting, okay? Suddenly there is someone call you. So then you will check, right? Who is this person? If this person is very important to you, and then what you will do, you are preemptive, you give preemptive priority to that person, isn't it? So your mom suddenly call you. So even if you are in the class, you probably will receive. Oh, give me your feedback. What do you think? Divi?
If it is our parents, I think the other person will understand, right? Because it's our parents.
Okay.
But if it the other person, I'm not sure they will like okay with that. They will maybe feel not important, I guess. And then
Okay, they will feel they are not important.
yeah, and also mm, I don't know. Maybe yeah, they will like
They will feel bad.
yeah, they will feel offended maybe.
Joy, you want to say something?
On situations like that, for example, we're in class offline or like we're in a meeting, I usually won't accept any calls unless they call me repetitively, like constantly. Then it means something's urgent. But if like my parents, they only call once, and I will usually recheck first. And if they call again several times, oh, okay, this is important. But then if it's like only once, I won't take it usually. I will just recheck. I'll text them like, talk to you later or something.
So not only calling, for example, you are conversing with someone, okay? Suddenly someone else coming, and then talk to you, and then you immediately attended to this new person. Have you often see this kind of situation?
Yeah, it's very often, no, especially when like it's someone's you're more close to or more attracted to, you will tend to just right away ignore the other one and talk to the new
To the
person
new
that just
person.
arrived.
So
Yeah.
this is giving a priority, preemptive priority rule to the new person. So then probably the person in front of you will feel bad because why they feel bad? Because uh, basically they will feel they are lower priority, right? Okay. So next question is what you supposed to do? If you keep smiling, what do you want to say?
Um, maybe for me, I will like list which one is more urgent. So it's not maybe it's not important, but it's urgent. Yeah,
Okay.
maybe something like that.
Okay. So how about you, Joy? You have certain
I don't think it's unavoidable. I mean, like it's like very human nature to like you tend to be nicer and like you tend to attend to someone you're like more close to, more attracted to. So uh the only thing we can do is probably try not to make it look so obvious. Just try to like okay, like be fair as best as we could.
okay. So giving priority to others is kind of normal things to do, right? So, but at the same time, there's a danger of unfairness, right? So that is the one that probably you need to think of. So even in the business situation, if you give a VIP, okay, that means you give a priority to others, right? So the others non-VIP will feel lower. Okay, then you probably need to deal with the unfairness in here. Okay, so before we go to the detail of queuing theory, you probably need to deal with that ethical situation first. Okay, so what is the candle notation that we will discuss today is this, yeah, MMS and PRP, yeah. What is this non-priority priority rule? Okay, so the input is the same, okay, using uh, arrival distribution is random, okay, and then the mean surface rate is also random with the mean of mu, okay, arrival rate is lambda, and then the number of surface channel is S. Okay. Now we have assumption here that the surface time distribution is identical, regardless their priority. Okay, and then all channel have identical exponential surface distribution mu. Yeah, remember, the the one that priority is only the uh, way of service. Okay? In terms of mu will not change because you are VIP, we will serve you better. In terms of the rate, no. Okay? It will not change the mean service rate. Okay, so with that, how to calculate is like this. First, you calculate UK. UK is the utility of its priority rule. Okay, so it is again the same. Lambda I divided by S times mu. Okay, so if you look at this, actually, this is rho, right? The lambda I per mu is the rho. And this is exactly the same formula as in MMS. Okay, but now we add K here. So this formula, you can put it into recursion. So UK is equal to UK minus 1 plus lambda K over K is the priority and U0 is the one that you put in as 0. And then you can calculate this rho as the traffic intensity. Okay. After that, you can calculate the waiting time per customer. Okay. So for each priority queue, you can calculate this. The formula is something like this, depending on UK, that means utility earlier, right? But we have a term, let's call this E. E is actually the this long equation here. It depends on the factorials and so on. And then for any customer, okay, you will have to calculate this formula using this formula. This WQK is in here based on this formula. Okay, and then for the LQ, again you use similar. Okay, and you can see the John Little formula still be used. Okay, exactly the same as other queuing theory. Okay, now let's do this example. Okay, suppose you have a clerk that have 4 types of tasks. Okay, one is urgent and important. Second is not urgent but important. The third one is urgent and lower degree of importance. And the last one is not urgent and low degree of importance. So this is basically a 2 by 2 matrix, right? Between urgent and importance, yes and no for each. Now, suppose you have 2 identical clerks, okay, and the number of tasks are the same. For example, for each type, it is lambda I is 3 tasks per hour. Okay, so based on Poisson distribution, while the clerk can handle 7 tasks per hour. What is this? This is the mu. This is the lambda. This is the mu. So regardless their priority. So this is exactly MMS and PRP. So then compute the MOE, measurement of effectiveness for each. So what to do? We check the number of channel here. We have 2 identical clerk, so that means S is equal to 2, right? And then we know that the arrival rate for each priority queue is lambda I is 3 tasks per hour, and mu is 7 tasks per hour. Then this is how you calculate. So first you set up U0 as 0, and then you put to the formula. Okay, this is the formula, right? Then you can calculate one by one. So because lambda k is given, S is given, mu is given, so you can calculate mu1. Okay, and then you can calculate from here. You can calculate mu2, mu3, mu4. U2, U3, U4. Okay, and if you calculate the ratio between each of these is actually 1, 2, 3, 4. Okay. So if you calculate the ratio, you will get the integer number 1, 2, 3, 4. Now, based on that, you can calculate the rho. Okay. This is remember in this case, in this example, lambda I is exactly the same, so you just calculate like this, okay, and you get the rho, and then you compute the E. Okay, so just plug in the formula. You see, mu is 7, S is 2, right? Okay, and then rho we keep this one, exponent to the S. So this is the rho exponent to the S, and so on. So and then you get E is 0.0565. Okay, then because we know E, we can calculate the WQ1, WQ2, 3, and 4. Can you see that? Okay, and now if you know each of these, then you can calculate the total for all tasks. So you sum all of that, okay, you get this value, right? And then the same thing, using the same method, you can calculate the L. And you can calculate the system delay and average number of customers in the system. Okay, because you put priority, so probably the system will become longer to the overall. It become faster to the VIP, okay, but become longer to the lower priority customer. Now, compared to this, okay, now look at this example. The next example is, instead of 7 tasks per hour, okay, what will happen if you have 6 tasks per hour? So here it is. If you calculate, okay, U1, U2, U3, U4, okay, U4 is 1.0, but remember, utility must be less than 1, right? So if the utility is equal to 1 or even higher than 1, this is not allowed. Okay, similar to MMS last time, right? The utility, which is lambda over S times mu, should not be equal to 1 or higher. Why? Because that means the queue will go indefinitely, right? So in this example, the last part, which is the task of not urgent and low degree important, will grow indefinitely and the system will become unstable. Okay. And now, if you look at this example again, do you want to calculate or just fine with this? Do you want to practice or you think this is okay for you?
We just need to put it into, right?
Yeah, you just need to put into the formula.
Okay, I think.
Do you have a calculator?
No, I don't have the calculator for this.
Okay.
Make it yet. Because this is a special, right? It's a little bit harder to make a special calculator. And
I'm a bit confused about the E.
E, okay, let's try to calculate the E. Okay, giving this computation, can you try first? Okay, because this E is almost similar to MMS. So, okay, let's try this. Let's try. Can you try to calculate E first? Okay, using this work, can you try to calculate E? And then if you have question, you tell me. Calculation of U is okay. The utility is fine, right? Do you understand the meaning of utility here, right? The utility of its priority queue. So this is the okay. So you remember last time, okay? 1 minus U last time was the how many times the server is idle. Okay, 1 minus U. So in this case, we have many U. Instead of 1 U, you have many U here. Okay. So depending on the priority. So first priority, second priority, third priority, and so on. And because of this formula, that that means the U is assuming already that the ratio is actually 1, 2, 3, 4 like this. Okay, so can you now calculate this E?
Like to the part until the sigma, I understand.
Okay, which
Sigma, I don't know how to. I'm really, that's why I'm not good at reading formulas.
okay, so you need to learn how to read formula. Okay, so U is mean service rate. S is the server, number of server, right? Okay, so rho is given here already. Okay, so rho exponent S minus S, this is okay, right? So S minus rho, this is 2 minus this rho is fine, right? And then S minus 1, so 2 minus 1, factorial. You know factorial, right? So n factorial is 1 times 2 times 3 times so on and so on until n. Okay, and then sigma is just sum. So you calculate the rho I, okay, rho exponent 1, exponent I divided by I factorial. Okay, maybe this is probably the confusing part. Okay, let's do that. I will create whiteboard. Okay. Create a whiteboard. Okay, so what is the formula? Okay, sigma of I equals 0 until S minus 1 of rho I divided by I factorial. What that means? So that means, okay, I is equal 0. Okay, when I is equal 0, what do you get? That means rho exponent 0 divided by 0 factorial, which is 1, plus, okay, rho exponent 1 divided by 1 factorial, which is 1 also. Right? 0 factorial is also 1, right? Plus rho exponent, okay, depending on S, how much is S? If S is 2, 2 minus 1, that means no more. If S is 3, that means exponent 2 divided by 2 factorial. Okay, plus rho 3 divided by 3 factorial. But in here, the S is only 2, right? So in that case, until 1 only. So this part is not computed. So, but rho 0, anything exponent 0 is 1, isn't it? And then so this is basically this is basically 1, isn't it? Because 0 factorial is 1. Anything exponent 0 is 1. So 1 divided by 1 is 1. Right? The second term, this one, rho exponent 1 is equal to rho itself. 1 factorial is 1. So in this case, you will get in here 1 plus rho. Now if S is 2, if S is 3, then you will get this term. If S is 4, you will get this term. So up to here, is it clear or not? The meaning of sigma is actually you put this term, okay, one by one, and then you sum. So you calculate this term first, okay, and then you sum all of that. And this term is summed up to this value. Yeah? That is the meaning of sigma. Clear? Okay. So, okay, I give you example again of, this is finished already, yeah? I delete, yeah? So, what is the sigma of I 3? Okay, of I equal to 1, 2, 4. Oh, can you calculate? Just to understand how to calculate sigma. That means this is what? The first I is 1. Okay, so you put 1 exponent 3 plus the second I is
2.
2. Very good. So 2 exponent 3. The third I is
3.
3. Very good. So 3 exponent 3. Okay. And then the fourth I is
4 plus 1, right?
correct. That is the
Okay,
last
okay.
one because that is the until 4. Okay. You see, yeah? So that's the meaning, yeah? So, okay, I'll give you one more time. Now I will give you another sigma here. Sigma, sigma, this is I, this is J, of Aij, okay? This is A equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, what does that mean? if you get this, okay, and you get A equal to Aij, oh, what is this sigma mean? Can you guess first?
You sum the row and the column. No.
Very good, yeah.
Oh, okay.
This is basically 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Right. So double sigma, that means now, okay, let's try another one. How about if I remove this one? What is the meaning of this? Oh, can you get this? So this will become VI equal. So what is VI? What is VI?
Sigma J means the sum of the column, right? So it will
Correct.
be a
So V, yeah, equal to 1 plus 2 plus 3 is 6.
6.
Yeah? 4 plus 5 plus 6 is 15.
15.
Yeah? And then this one 15 plus
24.
24. Yeah? Okay. So how about like this? Now W is sigma Aij of I. And this one, because this is sigma of I, this must be J. Right? Must be, right? So So what is that W? So W is here, yeah?
12.
Yes, this one is 12. This one is 15.
15.
Yeah? This one is
18.
18. Oh, very good. Wow. Super. You learn very fast. Right? So if double sigma, that means you sum of the row and then you sum of the column. Yeah. If J in here, you look at J. The J is the last subscribe. That means the column. Yeah. The first one means the row. Right. Of course, if you sum in terms of the row, that means this must be column. Right. If you sum in terms of the column, this must be row. Right. Of course, right. So with this, you can play with the notation already, right? Oh, next one. How do you put this into, for example, Python? Do you know? Okay.
So we never learned how to compute mathematical equation in Python, so we don't really
Oh, of
know.
course you need to learn that. That is.
Like to code
Oh,
something like a
okay,
program.
okay, okay. Let's do it in Python now. Oh no, this is my failure if you don't know this. Okay, really? I probably forgot to teach you this. Okay, you need to calculate this. Okay, open your Jupyter or your Python and then calculate this in Python. No, this is very important, because this is basic, right? So you need to know how to calculate uh, sigma and double sigma.
Yeah.
Okay, so
Oh, very printing dah.
sigma is just one sigma is just one for loop. Double sigma is two for loop. Okay, so let's do it. Okay, let me open. Oh, it's my failure. I did not teach you this. Let me open my spider. You can also open. Okay, let's create a new Python. Did I? Can you see the spider? Okay, so let's call A equal 1, 2, 3, right? And then 4, 5, 6, correct? And then let's put 6, 7, 8, 9. Okay. So now I want to get the sum.
Kita potong aja tas aja. Ini loh. Jangan.
So
Mana?
sum of row. How do you get the sum of row? So you will get 4. Okay. So for I in range. In this case, the number one is 3, right? So, yeah. So we put S equals 0. This is the sum.
Okay. Yep.
Then S equal to S plus A E comma C. Is that correct or not? So then print S. Okay, let's run this. J is not given, sorry. Oh, say, I want to get the J is number 1.
Sedih aku lihat hari.
The list. Maybe like this. Oh, okay. So you got 15. Okay. So this is basically, let's call this SJ. SJ. So now depending on J, okay, J equal to 0. Example, so I put this one J. Something is wrong. S. Oh, this one SJ. Okay. Now, is that correct? So this is 1 plus 4 plus 7, which is 12. Right? So if J is 1, okay, then you get 15 with this 2 plus 5 plus 8. Right? If J is 2, you will get 18. Is that correct? That is 3 plus 6 plus 9. Right. So now if you want to put it into a vector, right? V. Okay. So then you put it as vector. So you will put V. You can put VI or you can put V0 or VI equal to SJ. That is you want to append. Okay, you finally you can print the V. Let's try this. Oh, it's not. So we can put it like this. V dot append. SJ. That one will work. Yeah. So you get 3, 9, and 18. What is that 3, 9, and 18? I think something is wrong, right? Wait. I think the wrong thing is this one. Because we add. So if Sj is 0, without the phi is correct. Right? But the Sj must be in here. So this is the first part. When J, the column is, oh yeah, this is correct. 3, 9, and 18. So first one is 3. The second one is 3 plus 6, which is 9. And then the last one is 3 plus 6 plus 9, which is 18. But this is not what we want, right? What we want. What we want is I just need to get like this. Okay, so what I want is something like this. There. So when j is actually 2, I want to get only 18. Okay, I don't want to know 3, 6, and 9. So in that case, what I will do is I will create a new one. Okay, for j in range again 3. Now you will get this is the actual V. Yeah. The S0 must be in here. There. Is that correct? Is that correct? What is the meaning of this? Sj is, sorry, this is wrong. This is, must be J. This is the one that is correct. So 6, 15, yeah, 6, 15, and 24. 6, 15, and this is 24. So now this is the one that is correct. So in this case, I don't need this one. Can you get it?
Yes, I have a question. For I in range 3, what does range 3 means? Like what does it
Okay,
indicate?
so what's the meaning of 3? So let's do that. So I will copy this. Okay, and then I will print I. There. Range 3 means 0, 1, 2. Right? So if you put range 5, that means 0 until 4. Okay. So now can you make like this? But I want to get the sum of both. Okay, I want to get the sum of both, with this, the sum of rows and the sum of columns with this double sigma. So 1 sigma is actually this one. Okay, 1 for loop is 1 sigma. Okay, the second one is already this. Now, if I want to get the total, can you calculate the total? What is the total? Of course, the total is 6 plus 15 plus 24, right? $45. So can you devise a program like this? So I given A, I want to get the total with this double sigma. Okay, try to make it. this is the sum of its row. Right. Okay, so this is the sum of its row. Now I want you to make sum of each column. Okay. So this is a vector sum of each row. I want you to make vector sum of each column, and then I want you to make again the sum of rows and column with this double sigma. Okay, this is only. Oh, can you make this program? Where should I put this? So I can just put this sum of rows column. How do you? So if you want to make it more general, okay, so I will put m equal to the len of a. Okay, so if I give a in here, so I can put it a little bit more. Say for example 4, 5, 1. Okay, so let make it a little bit different. Okay, make it more general. So if a is this one, okay, so what is len of a? Len of a is 3. Okay, that means 3 rows. Okay, and then n is equal len of a0. Okay, so what is n? N is 4. So this is the number of rows. Number of rows, and this is the number of columns. Okay. So in that case, I is no longer 3, right? Okay, so what is I? I is a range from up to the number of rows, which is until m. Yeah. J is up to the number of columns. So, okay, let's name it differently so that not confused. So I will put it mr. This is mc, so that I will see. This is mr. I is until mr. This is until mc. Oh, there. Is that correct? So you get 10, you get 20, you get 25. Now I want you to make these two, sum of row, sum of each column and then sum of sum. So who will do sum of column and who will do sum of column, sum of sum? think it's important to know this so that you can use Python in your daily life. Familiar yourself. Anyone want to share? So let's call this W. Okay. W equal to empty, so that you will get the same. And then you copy. Okay. Right. But what you will get. You get W, print W. Okay, so what you have is SI. This is SI. This is SI. Oops, this is SI. So in that case, I must be there. There. Okay, let's check. Is that correct? No. No, because this is not SI. Okay. There. Is that correct now? Correct. Right? Oh, the last one. Come on. How about the sum of row and column? This is easy. Because this is just one number, right? You get only one number. How do you get that? So let's call this S or sum. No, I'll put it. Okay, let's put it S. Okay, so what you will do, this is easiest. Okay, so you don't need to put like this. All you need to do is just put S equal to S plus A. Yeah? So print S. Okay. Oh, sorry. S equal to 0. Okay. So when you run that, there you get that. Okay. So this is the sum of row. Okay, so this is again, I will write it here, sum of its row. Okay, here is the sum of its column. Okay, and then this is the sum of all. Okay, so when you run, you get that result. Okay, so with that, you are familiar with the notation sigma, right? With that, you can also deal with. So you're expert already, okay? Come back. Is it okay? You have any question? If you still have doubt, you tell me. Joy, you want to say something?
No, it's okay. But Python is very case sensitive and like the spacing
Oh,
gets
yeah,
sensitive.
you need to put it in the
Yeah,
spacing tab. That's why.
like the wrong tabs, then it have like different results.
Yes.
Yeah. This is my first time. No, the first time. Oh yeah, my first time doing maths in Python.
Oh,
I've
really?
never done maths in Python. Yeah.
Oh, it's my mistake. I supposed to give you this last year.
I think isn't this supposed to be on our first year with intro to logic? I don't think
Yeah,
you
exactly.
teach us.
No,
Yeah.
no, I'm supposed to give you in Python last year,
Oh,
right? So
but this also I'm also very weak at logic. Like there's
I
class
don't
right
think so. I don't think so. You're very strong in logic.
I'm quite bad in the class because we learn about loops and those kind of things, and I just can't like comprehend sometimes. Took me a long time compared to other classmates.
Oh, really?
Yeah.
No, I think I believe you're very strong in logic. The two of you. In fact, with Pancha also last time. I can sense you have very strong in logic. That's why I appreciate you. So try just probably you are not familiar only with the notation and probably long time did not use. So let's refresh ourselves with this because the next lesson we will use this again. That's why I need to.
Next one is Markov chain, right?
Uh, Before that, let's go to maximum entropy first, okay?
Okay, okay.
Let's, so, Livy, you want to comment on this Python and the sigma notation?
Maybe I kind of forget about the Python, so that's why.
Let's try to
Yeah.
use it again and again then.
Okay.
Okay, but you can get this, right? The sum of rows, sum of column,
Yeah.
sum of everything. No problem, eh? Okay, good. Oh, okay, good. So with this, you can just change this matrix, okay? You can just change this matrix with your own, and you can calculate. So the same thing with this priority queue earlier, okay? So you can also create your own program of priority queue. Okay. Or you want me to give you as assignment? No, no more assignment. So okay, so with this you can calculate E, and then you can calculate everything else. Okay, and now look at this next practice. Okay, see, a bank manager thinking to implement pre-fleet customer on top of regular customer. The question is, what is the ratio of pre-fleet customer per regular customer, so that the waiting time of each priority is equal? So this is very important question. You want to do fairness, but at the same time you create a priority customer, right? The waiting time is equal, but you start to create priority, but you want to have equal waiting time. Is it possible? Okay, so let's compute. Okay, so suppose the ratio of the privileged customer per regular customer is uh, this psi, okay, lambda 1 per lambda 2, and assuming that lambda is constant. So then we can calculate, okay, u1, u2, and then everything else we can calculate here. And then if their waiting time is equal, that then WQ1 equal to WQ2, right? Okay, but and then you put into the formula, okay, and of course you assume that u1 is not 0, right? So then you will see that this is not possible, right? You see this using this formula, you see this is impossible, okay? Unless u1 is 0, but u1 is not 0. So in that case, this value, okay, of chi, okay, there is no value of chi that satisfies both above equation. So in that case, it is impossible that the waiting time of each priority will be equal. So what's the lesson here? If you start to create priority, okay, and then you talk about fairness, that's impossible. Okay, when you prioritize, that there is no fairness. That's the meaning. Okay, so yeah, so if you want to make it more general case, so you can find this, and then you will see that will happen. Fairness will happen only when they are equal to 0. Meaning nothing, no arrival. That's why it's impossible. Okay, so I hope you understand this. So here, restaurant have 3 waiter. This is next practice. Okay, restaurant have 3 waiter and serve 5 customer per hour, and then the arrival is regular and special. Okay, so priority queue, and then special member are limited. So just a few number of VIP, okay, and then the arrival of regular customer is 9 per hour. So then the next question is, this is nice practice. Huh? What we don't know is actually the lambda 2, yeah, which is the arrival of the special member, such that the waiting time of the special member is only 1/4 of the regular customer. So this is allowed. Okay, if the lambda 1 and lambda 2 is not the same, so then you can set waiting time is a function of the other waiting time. Okay, so in here you see lambda 2 is 9. Okay, mu is the same. Support is 3. What we want to know is lambda 1, okay, and certain ratio that WQ1 is just 1/4 of WQ2. Okay, so with that we can just put it into formula. So we set alpha equal to 1 plus, of course, because you have only 2 categories, so W1 plus W2 here, divided by S over mu. What is this alpha? This is the last part here is actually utility, and then 1 minus utility. That means you are talking about the probability of idle. Okay, with this you can calculate everything, and you get W1 is 2.25 customer. Okay, so yeah, with that you can also get if you want to do more research, you can actually get this value between the intensity and the utility of the 2 priority customers. Similarly with the LQ. And E you can also calculate, and then you can make this graph. Okay, so the point here is if you use non-preemptive priority queue, okay, so basically what you set is the utilization factor, so that each priority queue in the proportion of priority of 1, 2, 3, and so on. Okay, if your lambda I is actually constant for all q. Okay, this is what we take here. Okay, so up to here, is there any question about queuing theory in general or this priority queue? So far, so good. You are okay? Okay, so in that case, let's continue with our next topic. Okay, on maximum entropy. We have discussed this last time a little bit during our class in Excel. I hope you still remember. But now I want to apply this to queuing. Can you open the slide in maximum entropy? Is it there in Lentera?
Yes, it's in Mandara.
Okay, good. So let's talk about this maximum entropy. Okay, and first is talking about principle, next about method, and then this is an optimization basically, right? Maximum of entropy. And if you want to go deeper, you can. But what I want to show you here is to demonstrate we can solve also queuing problems. Okay, and this is I want you to understand the meaning of invariant. Okay, and you can use this to do a lot of things, basically. Anyway, okay, so maximum entropy is initiated in 1957 by this person, Edwin Thomson James. He's a physicist. Okay, so and the last part of his life, he wrote a book about probability theory, logic of science. So you can also download this book. Okay, so the maximum entropy is just an interpretation of thermodynamic in physics. Okay, but later on, it became the part of Bayesian inference in statistics, and a lot of algorithm going on with this. So in essence, is a way to construct a prior distribution that satisfies some constraint. Okay, so what is it? It says that maximum entropy, yeah, is a statistical method to determine the distribution of maximum logical uncertainty about some parameter which is consistent with certain amount of information. Okay, so he stated that the probability distribution which best represent the current state of knowledge is the one that has the largest entropy. This is what we said as principle of maximum entropy. Okay, in context that precisely state with the prior data. Okay, what's the meaning? Okay, so the meaning is like this. If you don't know, okay, you assume uniform distribution. Hey, you already learned this during decision theory, remember? Laplace principle of insufficient. You remember that? Decision theory. In risk probability, you decision under uncertainty. You still remember? Right? If you don't know the probability, what you will do? You assume, right? You assume to be equal. Exactly this one. Okay? This is exactly the same. So, but now we generalize not just for decision theory, we use it for anything else. Okay? So you can model all that is known and assume nothing about what is unknown. And maximum entropy will choose automatically, okay, a consistent model with all the facts, okay, otherwise as uniform as possible. So if you don't know, assume uniform distribution. That's the in essence. Okay. So this is a general purpose method of making prediction based on incomplete information. Okay, incomplete information. So if you don't know, okay, or you know only partial information, then you can get it, even if you don't know. So very, very strong principle here. How do you get that? You assume uniform distribution. Okay, if you don't know, you still can get. How? Okay, based on maximum principle, maximum entropy principle, you can assume, uh, find the most uniform model subject to the constraint. Is it clear or not? Okay, let's try. Okay, so I supposed to have 4 slots here. Okay, so the slot uh, values are probabilities. That means the sum is 1, right? So given 3 slot, okay, what is the value of this last slot here in the question mark? Say I have 4 cells in Excel. Right? Okay, let me open the Excel. So can you see my Excel? I create a new Excel here. Okay, so you have 0 0.1, 0 0.05, 0 0.25. Let's put that. Okay, 0 0.1. How much the next? 0 0.05, 0 0.05, and then 0 0.25. So let's call this x1, x2, x3, x4. Okay, so the x4 is not known. Okay, I know the sum, right? The sum. So, oh, 0.4. But the sum of probability must be 1, right? So in that case, this yellow should be
0.6.
Oh, very good. So 0.6. Yay, you get 1. Okay, so that one is clear. Okay, so I know this must be 1, right? In that case, this must be 0.6. Easy, right? This is called degree of freedom in statistics. If you know the statistic, which is the sum or the mean, okay, and sum or mean have 1 degree of freedom. That means if you only missing 1 value, okay, you can get back that value. Okay. Now what will happen is instead of 1, I have 2. Okay. So instead of 1 now I have 2. So I have x5 here. And the sum must include up to x4. And I don't know this one also. What sum or the mean degree of freedom is 1. But now I go beyond my degree of freedom. So what is x4 and x5? Well, you can say, well, I will put 0.1. In this case, 0.5. Is it correct? Yes, it's correct, right? Oh, I don't want that. I want 0.25. And then this one is 0.20, 0.35. Correct also, right? So, what is the value of x4 and x5 in that case? So many possibilities. remember principle of maximum entropy. If you don't know, assume uniform distribution, right? So what do you get in that case? If you don't know, 0.4, 1 minus 0.4 is 0.6 divided by
0.6.
0.3, 0.3. Okay, so if you don't know, then this is the most probable value. Okay, okay. Then the question is, right? So 0.3, right? The question is this. Look, we have, okay, we have two unknown, right? With one equation. So the result is infinitely many solution, correct? Right? So in fact, this is a line. If you put x and y in here, so x plus y equals 0.6, that is a line, isn't it? Line equation. So which x is between 0 to 0.6 and y is between 0 to 0.6 or so. So now the value of 0.6 is obtained from the constraint equation, right? Because the sum of the probability is 1. Okay, and again we can set any value of x to get y. Okay, right? So, but the problem is if we set, for example, x equals 0.1, there is no basis. Okay, and then you will fight with each other because there is no basis. Why you set 0.1 instead of 0.2? There is no basis, right? So the maximum entropy principle is creating a basis for that, right? So we want to know what is the most probable value of x and y. The most probable of, okay, if you don't know any information, then the most reasonable assumption is they are actually equal. This is what maximum entropy is about. Is it clear now? Right? So again, now if you have 3 slots, what is the value?
We can just assume 0.2.
Yeah, actually that's the most probable value, 0.2. When you put 0.2 there, okay, 0.6 divided by 3, right? That means you assume uniform distribution, and then you will ask, why you set 0.2? Because it's based on maximum entropy principle, right? So 0.2, right? So if you want to be consistent, the most probable value, okay, is 0.2. Okay. Now the same thing here. Say you have this is another example. Yeah? You have y equal to a, b, c, d until e. Okay, and then you collect data. Okay, with input x that contain output variable y. So this is the conditional probability of y given x. Okay, now these are the constraints that the total conditional probability must be 1, right? 100%. This seems like more complicated problem than earlier. It is actually the same thing. You see this? Now, there are many possible combinations that satisfy that constraint, right? For example, if I put this one only 100% and the rest are 0, right? This is all 0, possible, right? The same thing, if I can put only these 2 are 190 and then these 3 are actually, this 2 is 10% and then the E is 0, this is also another possibility, correct? But again, when you put any numbers here, okay, all these possibilities are not based on the fact, right? So now suppose we know from the sample now that PE over X is 40%, okay? Then you set a constraint here, right? That A, B, C plus D is actually 60%. Again, you have many possible combinations, right? So then the problem is if you set any this combination, okay, you actually assume more than what you know, right? There are certain assumptions that you set. So what is the minimum assumption that you can set that everyone will agree about is actually the maximum principle, maximum entropy principle, right? So in that case, what you will do, you assume all equal, right? So in that case, you get 15%. The same thing, yeah. If you have additional knowledge that new data, okay, B plus C is actually 40%. Okay, what is, again, you have so many combinations, right? Then using maximum entropy, you can set that, and then you can actually get the probability that you want. Okay, assume uniform distribution. Is it clear or not? The meaning of maximum entropy principle. Okay. If in the beginning I did not give you this example, and suddenly I go here, you get confused, isn't it? Right? But when I go here and I give you earlier, then it suddenly is simple, right? So basically, maximum entropy, okay, principle is exactly the same as this one. Yeah? You remember Laplace criterion in decision making? Okay? Uniform distribution is actually the most uncertain. Okay? This is the simplest assumption that is consistent with the data and the problem. Okay, so because of this, there are many names, okay, different names for various centuries. Okay? They also call it as Bernoulli principle of insufficient reason. They call it Laplace criterion, principle of insufficient reason, principle of indifference, okay, and so on. So basically, this all of this principle that they talk about in many centuries is based on maximum entropy principle. Okay, so here it is. When we solve a problem at hand based on the most reasonable assumption that they are equal, okay, they actually use what is called maximum entropy principle. What is that? That the probability distribution which best represent the current state of knowledge, okay, is one with the largest entropy, okay, in the context that precisely state prior data. What is that connection with the maximum entropy anyway? Okay, let's do it in Excel again. Okay, so I don't know this one, right? So this is x4 and x5. So in that case, I put 1 and 1, or I put 0 and 0, that's fine. And then what I will do is I calculate probability. Okay. So the probability is, okay, I calculate probability. The probability is what? This one divided by the sum, isn't it? Correct? So I will put this as no change. So that the sum is, the sum of probability is 1. So I can put any numbers here, but I can calculate as probability. Okay, so you can see. Okay, so this is probability, and then what I will calculate calculate is actually entropy part. Okay, so I will calculate entropy part here. Do you know what is the formula of entropy? The entropy is minus, so equal minus this one multiplied by ln of this one. Right? Entropy is the sum of that. Okay? But there is a problem here. Okay, so if the probability is 0, you put it as 0. Okay, so I put if this one is less than equal to 0, then 0. Otherwise, put that value. So that is to calculate the entropy. So then you calculate the entropy itself. It's just the sum, yeah. The entropy. It's just the sum of the entropy part, yeah. Okay, so what I will get, okay, I will use solver. Okay, so what I want to do, I want to get to set the entropy. Okay, let's name it so that you will see. This is the entropy. Let's name this entropy. Okay, so I want to get the solver. Okay, I want to maximize this entropy, changing cell, the one that in yellow. Okay, subject to constraint, that the sum is equal exactly to 1. Okay, and then you solve. Oh, got that. Oh, look. Bam, bam, bam. You will see this is exactly 0.3. What does that mean? What does that mean? Okay. Maximum entropy, okay, is now becoming, from the principle, now becoming an algorithm. Can you see that the meaning of this? So earlier we said, okay, the based on the principle of maximum entropy, okay, or Laplace principle of insufficient reason, this must be 0.3, right? But look, if you have a problem and you said this is 0.3, this is a simple problem, then you can solve it that way. But when your problem is complicated, you don't know what to do, right? Then you need an algorithm to solve, to get exactly that problem. Okay? How to solve that? How do you calculate using a computer to get that result? That is exactly what we are doing here. Is this clear or not? Okay, so using maximum entropy, okay, if we don't know, we assume uniform distribution, right? But that is the principle, okay? Now, maximum entropy method is a way to formalize that principle of insufficient reason. With that, okay, you suddenly, the way to formalize is to create a mathematical optimization, right? So basically, this is the bridge between the principle of sufficient reason and an algorithm to solve our problem using computer. Okay, so earlier this is what I just did in Excel, right? Find P, okay, by computing the entropy and then maximize it, okay, subject to this constraint. Correct? Right. So okay, if you want to, because you are already having this, right? This optimization, of course you can calculate mathematically. Okay, so if you want to calculate mathematically, you remember how to calculate. What is this? This is the, you can calculate using Lagrange multiplier. In the beginning of our class in OR, we discussed Lagrange multiplier, remember? Right? So how do you calculate Lagrange function? Okay, so you want to have maximum entropy subject to this constraint. What you will do, you get L, yeah? L of pi of lambda, right? So in that case, you set the constraint, okay, with this one, sigma of pi minus 1, multiply that with lambda, and then the objective function, which is this maximum entropy. Okay, you put that together, and then what you will do, you set the, okay, the Lagrangian function, the first derivative to 0, okay, subject to the two parameter, which is pi and lambda. And if you calculate this, okay, you will get exactly this value. Okay, so then the next question is why we need to do optimization. Okay, why should we make a simple problem above, okay, into more complicated formulation of maximum entropy, right? Well, the sample that I give you is really simple, okay, but once you make the problem into an algorithm, okay, so you can solve any problem at hand of any constraint optimization. Okay, you can solve it using computer. This is very powerful, right? So once you can translate the problem into an algorithm, then you can solve the problems automatically, okay, by computer. Okay, so this is the, now instead of probability, you can also put it as flow here. Yeah? So you can put any number. For example, the sum is 150. Okay, and you know that A is 5, B is 25. What is the value of C, D, and E? Again, you can put into maximum entropy. Okay, so I put it in Excel here. We know that the sum is 150, A is 5, B is 25. Let's put that. A is 5, B is 25, and now I have 3 that I don't know. Okay, so I will put 1, 1, 1, but I want the sum should be 150. Here is just 33, right? So how do you solve that? The same thing, okay? So you go using solver, okay, right? So what all you need to do is to change this, now this 3, right? And then now you edit this so that the sum is not 1 but 150. Okay, so the sum is 150. So, and then we click OK and solve. Okay, you get the solution with this 40, 40, 40. Okay, any question? Simple, you can do it, right? Okay, tell me what you just learned so that I can get your feedback. Tell me. What is this maximum entropy? What is this maximum entropy principle? If you want to use Python, I give you the code. Can you see in the slide also, I think. Okay, so you need to import this one. Okay. This is called constraint programming, CP. Okay, and you can use constraint programming to solve maximum entropy. Okay, and just copy and paste this. Okay, so if you want, next, I want to show you, okay, this is the nice thing. Okay, with this very simple example, I will show you how to use maximum entropy to solve queuing problem. Okay, so you will see, okay, how the maximum entropy is actually related to maximum efficiency. See, remember, okay, that in traditional queuing is waiting line. Okay, now I generalize it as a process where people, material, information need to wait, okay, at certain time to get the service. So basically, queuing is just demand plus supply. Yeah, in the system, okay, where there is a transfer of information, material, or people between the demand and the supply, yeah, between the customer and the server. Okay, so say you have a queuing system like this, 1,000 customer, okay, and service time is 1 minute per customer, and you have only one server. Then the question is how long the queuing be, right? So I can draw this. Can you see it? So you have 999 customer, okay, and then one customer being served, right? Because you have only one server. So 1,000 customer times 1 minute per customer, so you will get 1,000 minute. How much? That is 16 hours and 40 minutes. Yeah, this is crazy. So based on the queuing rule of thumb, okay, you remember this, right? So we will now employ this queuing rule of thumb. You have N is 1,000, okay? The R is the service time per customer, S is the number of server, and then T is the total time to finish the queuing, right? The delay. So this is basically the system performance. So let's come back here. Suppose instead of one server, you have 100 server. Okay, how long the queuing be? Okay, again, the service time still the same. So now what you will do? Okay, how long the queuing be? That means the T, right? N is 1,000, R is 1, the number of server is 100. So you get T is 10. What that mean? Okay, so that means if you have 100 server, okay, the queue will be 10 customer, isn't it? Divided by 100. For each line, you get 10 customer. Correct? So in that case, 10 customer time 1 minute. Oh, suddenly you get only from 16 hours. Okay, this queue will finish in 10 minutes. Cool, right? So that is the beginning. Yeah. So what is the meaning of division actually? When you divide something, okay, A divided by B equals C. Okay, anytime you divide something, you actually, there's a hidden assumption that you divide with a, so that the distribution must be uniform, isn't it? Do you understand? The meaning of division is actually you divide it so that it'll become uniform distribution. So you distribute the customer equally among all the servers. Okay? Remember 1,000 a while ago. suddenly you divide by 100, you get 10 customer. What does that mean? That means you divide, okay, equally among all the server. That means distribution is uniform. Okay? Anytime you divide, you remember, you assume something behind that, which is uniform distribution. So next, I will show you, okay, that the uniform distribution will produce the most efficient system. Okay? So let's make an extreme distribution example. Okay? So again, you have 1,000 customer, okay, and S is 100 server as before. And now this is not uniform distribution. Okay, 99 server will only serve one customer, and then one server will serve, this is priority customer, right? So one server will serve the remaining 901 customer. How long the queuing be? Something like this. How long the queuing be? Now you understand the meaning of distribution now. Right? If your distribution is not uniform, what will happen? It's not efficient. Right? Can you see? How long the queuing be? Of course, 1 minute times one, the maximum, isn't it? Not one. Even though this is finished and then they will be idle. And this, the total queue is actually 901. Correct? Okay, the queue will last 901 minutes, even though you have 100 server. Why? Because they are not uniform. So uniform distribution is actually the most efficient system. Can you see that now? Why? Because they are actually, this is extreme, okay? After they serve, they are idle. Interesting? Okay, why distribution matter? Can you see that? Remember, server is basically the supply. The customer here is the demand. Can you see that or not? So distribution matter, isn't it? So if you make it uniform distribution, you can finish it in 10 minutes. Okay? With the same number of server, 100. If you make it not uniform, what will happen? Okay. Now, if the customer are not distributed equally among the server, say for example like this, how long the queuing be? Of course, depending on the maximum queue number of customer, isn't it? Right? The queuing, the maximum number of customer is the how long the queuing be. Even though you have the same exactly 100 server. In that case, you understand now that, look, uniform distribution is the most efficient. Right. Wow. Now you start to understand the delay in this case is the largest number of customer, right? And of course, because they are not uniform distribution, whatever it is, okay, I don't know the non-uniform distribution, so I just know that they are not uniform, then must be larger than 10, right? Because why? Because if uniform is exactly 10 divided by 1000 divided by 100, right? But if you are non-uniform, there must be less than 10 and the other one is more than 10. In that case, not efficient. Okay? The queuing of non-uniform distribution is always longer than the queue of uniform distribution. Understand that? Okay? So then you understand that the uniform distribution, this has become theorem. Yeah? The uniform distribution of demand in the system would make the most efficient utilization. Do you get? Okay. When you do a maximum entropy, you create a maximum distribution. What is that? You create a most efficient utilization. Do you get it now? The principle of this. Okay. So, okay, the most efficient utilization will be the minimum maximum queuing time in this case. Okay. And the most efficient utilization happen when the customer are actually distributed equally. So, two things to take away. When you divide, you assume uniform distribution, isn't it? Hidden assumption. Okay, and you know, based on this simple example, that uniform distribution is actually the most efficient utilization of the system. Okay, so this is just a proof by contradiction. Yeah, assuming that uniform distribution is not the most efficient. So in that case, the delay is the maximum waiting time in the system, right? And you assume, the assumption implies that the delay must be greater than the mean of uniform distribution. Then the delay must be less than the uniform distribution. However, okay, because it's not uniform distribution, then the some value must be larger than the uniform distribution. Okay, okay. In that case, the delay must be larger than the uniform distribution. This is contradiction. Okay. In that case, the conclusion is yes, uniform distribution is the most efficient system. Right? Simple proof. Okay. Okay, so this one we will discuss after lunch. Okay, so let's meet again. So along our lunch break, I updated the slide of maximum entropy. So you can refresh the slide. Okay, so welcome again. Livia, are you there? Okay, so let's say our scenario that we have earlier. Okay, so we have in here, we talk about meaning of division, right? So this is the review, I hope still remember. So every time you divide, there is a hidden assumption that the distribution must be uniform. Okay, so say you distribute, example, you distribute the customer equally among the server. That's the meaning, right? So if you have 1,000 customers and then you have 100 server, that means the queue length will be 10 customers, right? So and then we try very simple scenarios that if you have extreme distribution of example, okay, that 99 server will serve only one customer, while one server will serve remaining 901 customer. That means how long the queuing be. Of course, the queuing will be 901 because R is 1 minute per customer. Okay, so.
Sir, your voice is a bit low.
Oh. My voice is low. Let me get the setting in that case. Oh, okay, that's fine. Oh, now it's better?
Yeah, it's way better. Okay, thank you.
Okay. It keeps changing automatically. I don't know why. Okay. Now okay? Okay, so when we have extreme distribution. Okay. So you will see, even if we have earlier using uniform distribution, we get 10, right? So of course, if you have only one server, that is 1,000 customers times 1 minute, that's in 16 hours. Okay. But if you have 100 server with 10 customers, that's only 10 minutes. Right? You want 100 server, you get 10 minutes. But if you make it different distribution, okay, with this extreme non-uniform, okay, with a peak like this, okay, then you will see that the queuing will become too long. Yeah? It is 901, right? And any unequal distribution, if you see this drawing, any unequal distribution, that means unequal means some will be less than 10 in this case, some will be above 10, correct? Otherwise, if everything 10, then exactly uniform distribution, right? Okay. But when we said unequal, that means some, I don't know how many, will be less than 10. Okay. Some will be above, correct? So in that case, the queue length will be based on what is the maximum number of customers. Okay. So then because some is less than 10 and some is above 10, that means the queue length will be longer than 10, correct? Right. In that case, we can see, okay, that unequal distribution is actually less efficient in terms of utilization, yeah, compared to equal distribution. So that's what I want to say in this slide. Yeah? So in terms of utilization, okay, arrangement of the queue length, in this case, utilization, uniform distribution of demand, okay, will be the most efficient. Okay, so this is one of the simple proof that maximum entropy principle works in practice. Okay. So, and if you note earlier, we have fixed number of demand, say 1,000, okay, and then we have fixed number of supply. Yeah? So fixed rate, so R is 1 customer per minute or 1 minute per customer is the same. So and then fixed number of server, S is 100, right? So, and what we vary is actually the queue length distribution. Because of this variation, okay, then we produce delay. So various delay with this maximum between the queue length times the service rate. Yeah. What is the queue length? Is the number of customers. Service rate is the minute per customer, correct? So and then the unit is correct. So the delay is minute. Okay, if you multiply. So in the next scenario, okay, we will fix the number of demand, same, but instead of 1,000, okay, I will put it just 30, and then we fix number of server. Instead of 100, I make it into 3 only. Why? Because I want to do the detail of each of them. Okay, and then what we vary is in here is the supply. Okay, so we supply, we change. Okay, so suppose you have 30 customers. So in this case, you have demand and supply. Okay, case. So demand is 30 customer and okay, and then the number of server is 3. Yes, yeah. The service time, let's make it a little bit bigger. So 2 minutes per customer so that you can see. So earlier we know that if you distribute equally, right? Okay, That means 30 divided by 3. That means 10 customer, correct? That means maximum delay in this case is 2 minutes service time multiplied by 10 customers. So total is 20 minutes. Okay, so let's call this base case. Okay, remember, put note in your paper. Base case is 20 minutes. So can we beat this base case? Can we improve our performance against the base case? Okay, so let's try. Okay, so remember, this is the base case. So you have 10 customer and then 3 servers, so 30, right, total. Is it clear until here, the base case? So maximum delay is 20 minutes. That's what we have, the P. Okay, now our practice now. Yeah. So what we vary now is the service time. Okay. Server 1 is 1 minute per customer, service 2 is 2 minutes per customer, server 3 is 3 minutes per customer. Okay, so of course we put it into batch. Customer arrive in once in the batch, it is 30 number of customer per batch. So distribute this customer to each server so that the maximum total queue will be minimized. Can you do it in Excel? Okay. So if earlier I put equal, that's easy. So your challenge is actually, okay, if you can do this during our lesson, then it's fine. If not, it will become your homework. Okay. So do it now, otherwise it will become homework. I know you hate homework. Okay, so how to do that? I will show you. So 30 customer. Okay, again you have equal demand. Okay, so let's do it. Server 1 is 1 minute per customer. Server 2 is 2 minutes per customer. Server 3 is 3 minutes per customer. So I put here server 1, 2, 3. Okay, simple table. R1 is 1, R2 is 2, R3 is 3. 3 minutes per customer. R is the service time. Okay. Say I put equal. Okay. Let's make equal demand. Okay. In this case, demand is 10, 10, 10. Right. Of course, the queue time is what? Because it's 10 multiplied by R. R is 1, right? So 10 times 1 is 10. Okay. And then R is 2 times 10 become 20. This one, R is 3. Multiplied by 10 become 30, right? So what is the maximum queuing time? 10, 20, 30. Maximum is 30. Oh, this is worse. Okay, why is it worse? Look, I thought earlier we want to put equal demand. No, equal demand happen only when you have fixed service time. But now the service time is not equal. Okay, so in that case, if you put equal demand, it's not better. Oh, remember, earlier we fixed the demand. Okay, we fixed the server. Okay, so you change the utilization only. Okay, but here the service, okay, is changing. Then our method earlier is not working. Actually bigger than 20. Right. So now question is, can you change this number of number of customer in each server so that the total queuing time will be minimum? Do you get the idea? Do you get the problem? Okay, I'll give you an example again. Okay, so say I distribute it this way. 15, 10, 5. Remember, total is 30, right? 15 plus 10 plus 5 is 30. Okay? So, what happened? So, 1 times 15, 2 times 10, 3 times 5. So, the maximum is 20. Oh, in this distribution, this is a little bit better, right? What? It's exactly the same as the base case. Uh-huh. So next, what happened if I change a little bit, okay? Instead of 15, 10, 5, I will change this, okay? Trial and error, huh? So 19, 8, and 3. So 19, 8, and 3. What you will do, you calculate, right? So 1 times 19, 2 times 8, 3 times 3, yeah? 9. So what is the maximum? 19. Oh, 19 is a little bit better than 20, right? Yay, we improve. Okay, I found a better demand distribution, which is better than the base case. Wow, you're happy with this? Not yet. Can we improve from here? Okay, let's improve. What if we a little bit change down? Instead of 19, we put it 18. Okay, so because this is 18, we total is 30, right? So then I can put anything. Say I put 8 and 4 in here, so that the total is 30. And then we multiply, 1 times 18, 2 times 8, 3 times 4. Oh, again, much better. Now is improve. Huh? Instead of 19, I improve to 18. Oh, okay. Can you improve better than this? What is the best? You make an Excel. Simple. Okay. When you finish, you share. You share your screen. Sure, sure.
I don't think, I think it's 17. I cannot find anything faster.
Oh,
It's like,
yeah. 17. Oh,
is there anything faster
yes.
than 17?
Yes.
Okay, wait, give me a moment.
17 is 1785. Is that correct?
Yes.
Yes. Okay. So question is can you improve better than that? And question is, of course, this is you do it manually, isn't it?
Yeah.
Oh, that's the problem. Okay, so I want you to
Oh, solver.
automatic system. Yeah, how do you solve?
Okay. I use solver.
Okay, can you formulate the optimization of this problem? Oh, interesting. Because if you can make it optimization, then I can change the value, right, later. Okay. Otherwise, every time you change value, you you look at it one by one. Oh, again, this is not systematic. Trial and error, right? How do you solve this systematically? Yeah, so I put that in the slide. Many possible configuration and of demand among the supplies, right? So yes, trial and error works, yeah, but unsystematic. So the question is how to solve this problem as optimization. Okay, so that you can use solver, right? Well, you have solver in Excel, I know. That's the question is now suppose you have a real world problem like this, how do you solve? Right, that's the most important part, right? So that you can apply in real life, right? again, I said this is this may work for a small number of server, right? To be server, but it takes long time. Okay, we need more systematic procedure to solve this problem as optimization. Yeah? So we not get exact equal distribution. Yeah? So the question is, because this is discrete, so we want to approach this to all uniform, uniform distribution. So how do you use this? How do you solve this? So one approach that so I give this problem to my previous students. Okay. Actually, they are PhD students. Okay, so what happened is they try this, they make it this. Okay, total queue length, I know that total queue length is this one, right? N, the number of customer, times the time, R, right? And then what they do is find Ni, okay, so that minimum of this one, subject to constraint, the total is 30, right? And then N is discrete. So, oh, can you try this in Excel? So let me try. Okay, let me pick a new sheet here. What do you get? N, I. This is I, and then R, I. Right. So this is the one that we want to get. So then yellow. So I is 1, 2, 3, right? And then say 1, 1, 1, and then the sum. This must be 30, right? Sum of this one, and we know this must be 30. So this is the green one. And this is given. R is given. So I put constraint orange here. So here is 1, 2, 3. This is given. So T, I is just multiply, right? This one multiply by that. Okay. So in here, so we get Ti. So we want to minimize this Ti, okay, subject to constraint this one. So with what happens if we do that? So what is this? Minimize the sum. Okay. Minimize the sum. So let's do the sum here. Sum of this. Okay, so this is the attempt to solve this problem. So let's put it in blue so that you know this is our goal. Okay, this is our objective, right? And this is our constraint. Yeah? Okay, so what happened? Go to Excel, we solve this. The objective will be this one, and we want to minimize by changing this yellow. Okay. And then subject to constraint that the sum must be equal to this one. Right. So you make it integer, that's fine, so you just solve first. Oh, we get the solution. Oops. What's the result? Extreme distribution, which is 30, 0, 0. And the T is actually 30, which is larger than 20. Oh, no, no, no. This is not what we want, right? So, wrong way of optimization. Okay, now you solve it. So how to, I just give you the wrong way. So you need to solve it the correct way. Easy to find a wrong way of optimization, right? That's why I put that attempt, you know. Okay, so I will not record.
But the
Okay.
thing is, I don't use max entropy, but it's wrong. So I try to solve it by I want to have the minimum maximal queuing time, so I just so I set it as the objective. Then I
Okay.
minimize, and then the constant I change the variable is this one, the n.
Yes,
Then the
correct.
constraint is e6, which is the sum.
Yeah,
The
correct.
sum 3n is equal to 30,
Okay.
and then everything must be integer.
Yes.
I
When
think
you
it would be,
solve it,
but it doesn't work.
you get 30.
Yeah, that's why.
Oh no. This is actually worse because remember our base case is 20.
Yeah, that's why.
Oh, so how to solve this?
Yeah, we should use max entropy.
So, okay, you want to use maximum entropy, but question is, the formula of entropy is probability multiplied by the ln of probability, correct?
Probability multiplied by the
Yeah, entropy is sum of entropy part. Entropy part is probability multiplied by ln or logarithm of probability.
okay. So
Okay, so the question is, how do you calculate?
how do we calculate the probability?
Yes, how do you get the probability out of these numbers? How do you get probability? That's the most important part is there.
Can we not just assume 1 divided by 3?
What? How do you get, for example, which one is probability? Okay, let's assume something. What is your assumption?
Probability must be distributed uniformly.
Probability is
Must be uniform distributed.
yes, but what is that? How do you get probability out of these numbers that you have?
Service time. Can we?
Okay, try.
So like since it's 6, so 1 divided by 6, then multiplied by this one.
Okay. The sum must be 1. Some probabilities must be 1. Okay.
Or we can just assume everything is 0, 0,33333.
Okay, you can try. You can try and then solve it.
Wait, I just type
You can assume
everything.
anything and then try. And then let us see.
Wait, the formula is probability multiplied by ln probability, like this, right?
Yes, that is minus.
Plus,
Minus.
oh, minus.
Sorry, the whole thing is minus. Negative, yeah. Okay. Okay. No, just close it. Or you want to calculate one by one? That's fine, yeah. Okay. Again, multiply by ln of that probability plus the last one. Probability ln of that t. Okay. So now you want to minimize this. Maximize. You want to maximize this. Sorry. Maximize this. That's fine. That is okay. And okay,
Oh no.
still the same. Why? Something wrong with the probability.
Okay, we just try. Uh,
It will not work.
probability.
Yeah.
Uh,
Uh, the probability must be a function of that you know.
It's most likely that one will have like the highest probability actually.
Let us see. How do you get that?
Can we flip the before? Okay, wait.
You can.
Uh,
You can try, okay? This is interesting problem.
30. Yeah, it's very likely that one has the highest probability, no?
How do you make it highest probability?
Hmm.
Hmm,
Or can I just randomize?
randomized. Okay, you can try.
Wait.
Joy have Joy is very creative, so there's a lot of ideas. Where did that come from?
I just flip it. So it used to be here, right? So this one will have the biggest one.
It will not work. You know why it doesn't work?
Why?
Because your probability does not depend on n.
Oh, it depends on. Oh, it needs to be a formula.
Yes.
Okay. One divided by. Oh,
That one might work. Okay.
loh. Okay lah.
You know why it doesn't work? Because you divide by 0.
Yes, I just add random.
Error. Yeah, the sum of probability is not 1.
Oh wait, I just add to solver lah. This one.
Okay.
I think my solver is broken.
No, it's not the solver.
We change this one.
Yes.
Cylinder cell
No
equals
need
to
to make
30
it into series file.
equals to 1.
Okay.
Yeah, should work.
No.
Probability.
This is very funny. Okay. When you try to make like this, okay, try to think systematically. Okay. Okay. So I will tell you something. let me share my slide again. Okay. So earlier our optimization result is like this, right? So you get 30 and 0, 0, so worse than our 20 base case, 20-minute base case. So it's clearly wrong optimization. So here is the correct optimization, okay? To get the correct optimum solution, we need an index, right? What is this index? Because we want to create a maximum entropy, okay? So we want to have an index that would represent the best result when the distribution is uniform. Okay, uniform distribution mean what? Invariant. It means does not change, meaning equal. Okay, so that index is called entropy. Okay, therefore the technique is called maximum entropy. So you know that when the entropy is maximum, the distribution is uniform. You know that, right? So how to get the entropy? Entropy is computed as, this is the formula of entropy, you know that also, right? Over S, okay? So all the possible value of P, okay? And you know the total Pi is 1. But our problem is how to get the probability, okay? So to get the probability, remember our goal is to make the probability uniform distribution, right? In that case, what do you want to make it uniform? That the one that you want to make it uniform is called invariant, okay? Because we have demand and supply, okay, and the total queuing time is computed this way, right? Then what you need to do is to compute the probability as Ti divided by the sum of Ti. Okay, in that case, the same as n times r divided by the sum of n times r. Okay, with that, you will get Ti is as uniform as possible. So this is your maximum entropy formulation. So you maximize the entropy subject to the sum of demand is 30, right? So very simple. So when we put that, okay, we want to find N1, N2, N3 so that the entropy will be maximized subject to this constraint. When the entropy is maximized, you will get this condition. Yeah? N1 times R1 equal to N2 times R2 and so on. Yeah? So this is what is called uniform distribution. Okay, so when you try that, okay, this is what you will get, okay, if they are not integer. So you will get this 16.4, okay, and the total Q is actually this value, okay, if you don't set as integer. Of course, if you set it as integer programming, you will get 17. Okay, so if you set it as integer, oh no, yeah, 16. I will get 16. This is the 16, 8, and 5. This is the, and you will get 16.3. Okay, try this. Okay. So here I tried by manually a while ago, and this is the things that we can try. Oh, entropy ratio. Entropy ratio is the entropy divided by maximum entropy. Maximum entropy happens when the probability is equal. Okay. Okay, try that in your Excel. Can you? And then you share your screen.
Wait, sir, I have a question about the probability. So the probability is Ti, so the total.
N times R, Ti is N times R, right?
Yeah, divided by sigma.
Yeah, probability
TGS.
must be that value divided by the value.
Okay, okay.
Okay, so of the same variable, total value of the same variable, that is the probability. Okay, so in your case, you just put it. Now, if you have a problem, you can calculate using part. Okay. Okay, you want to share your screen?
Sir, can I share my screen?
Yeah, go.
I have a...
TV.
Okay, wait. Let's move it.
Okay. So this is your R.
Why it is...
Okay. So let's do this. Can you go to B3?
B3.
Okay, that's correct. And how do you calculate probability? B3 divided by that one. Correct, correct. So now can you put in A6 entropy part? A6.
A6.
A6. In A6 you type entropy part.
Oh, entropy
B part.
part.
Okay, and then there you will put first you can calculate entropy part, which is equal to negative of
This one.
yes
Times
multiply the ln of that one.
of this one, right?
Correct. Okay, enter. Okay, wait. Before you copy, so there is a problem in here when you your probability is 0. This one become error. You can copy to until 3. What will happen? You will see there's an error there. Why? Because when your probability is 0, ln 0 is not computed. Okay, so in that case, you can put if. So you go to B6 again. So you put if. Okay, if open parenthesis, that probability B5, if B5 is less than or equal to 0,
If B5 is
less than or equal,
less than or
and less than
oh yeah, less than
equal to 0, comma,
comma
0,
0.
0, comma, yeah, then 0, right? Comma 0, and then comma again, that one you close. Okay. Now you press enter and then copy. Right, now you can 0. Then the entropy is the sum of this entropy part.
Okay, so
Sum of this. Okay, close it. Okay, now you can run again, solver. Maximum entropy, okay. B until D, correct. And then E is the sum, correct. Okay, run, solve. There you go. Okay. So the total is 16, 16, 8, and oh yeah. If you try remove the integer constraint, you will get a better result.
Okay, I will try to
The constraint of integer, the 3 integer. It is delete.
so
When you solve, you get 16. Yeah, that's correct. And you see the total Q n times R is exactly equal to each other. Can you see? That is the invariance. Yeah, that's the invariance. So this one you don't need to put the total. What you need to put is the maximum. That 49 is not so useful. That one you don't sum, you put the max instead of sum. Max. Maximum of equal max.
equal max.
Yes. Maximum of this B3 until D3. Okay. So that one is the, so you can see, yeah. So, oh, this is the entropy is very small in this case. Yeah?
How do you try to run it?
What happened?
I try to run it again.
Oh, when you run it again, you get much higher. Yeah, because solver in Excel is having depending on initial condition. So your customer n initially you can put 111. It's fine.
Um,
The one in yellow.
oh, this one.
Yes.
1,
And then 1.
1.
Okay, and then you can run. No? Something is wrong. That's strange. Something is still wrong in your computation. Why become like this? See,
Oh, I know. Wait.
in your total probability is not 1. The question.
Yeah. We change it into maximum.
Ah, okay, that's
It's supposed
why.
to.
Okay. No, okay, so, okay, correct. So the one a while ago is sum, right?
Yeah.
Okay.
So I'll change it to some. Here. Yeah. That's the probability.
Okay, so you need to put the maximum in G3 maybe.
Okay, C3. So the maximum is.
Okay, can you run again? Ah, okay, this is the correct solution. So 16, right? Okay.
Okay.
What happened if you put the integer? You solve for
And then put all of
add. You can add, and then
which one?
you can put B3 until D3, and then put that integer. Yes. No need you can just range the whole range. You can put it as integer.
Oh.
So B3 until B2 yeah, B2 until D2.
Itu C2.
Yeah, it's okay. Right. So if you put that integer, you will not get 16. Yeah? You get 18. So that is actually integer programming in this case is not working well.
Oh, I still got 17.
You can still get 17. What is the initial value?
Okay.
I think so.
It's 17, 6, and
Last time I got 17. What is your value? You want to share your screen?
oh no, wait, why does it got messed up? It worked before. I got 17. Wait.
Run. Why there is an error?
I don't know. It was working before. I got.
I think you need to calculate the entropy part first, because this error happened because your probability, some of your probability is 0.
Oh, I got 17 before. I don't know why it's 16 now. Oh, by the way, so it works like this. Like without the maximum entropy, it also works.
Oh
Last
yeah.
time it didn't work because I used simplex.
Oh yeah, simplex. Okay.
Yeah, like if this is 30, wait,
Okay.
I was checking before whether it works or not.
And okay,
This one shows 17.
what do you maximize or minimize?
The objective,
The objective is maximum of.
the delay time.
Oh, okay. That will work also.
Yeah.
Mm,
Yeah. This one before was 17. I don't know why it's 16 now. Like it was the exact same with this one.
okay. So yes. So if you put maximum delay time, yeah, you get 17 also. Very good. Yeah, without maximum entropy, you can also get, right? Okay, very good. So I hope you start to uh, remember this result that you can do optimization, okay, using solver. Okay, one way to use that is to create maximum entropy. Okay, I don't know. I got 17, 8, and 5 using my solver. Do I? No, this is not. Okay, anyway. So what happened is let's summarize. Okay, uniform distribution of the product. Yeah? The T in here is actually N times R, right? N is represent the demand. Okay, R is represent the supply. So the uniform distribution between the product between demand and supply in the system will actually make the most efficient utilization. Okay, so and this result can be achieved using maximum entropy. And so if you look at this, now I can conclude this. Yeah? So I can call this a principle of efficiency in utilization. Okay? Okay, the system is efficiently utilized when the demand and the supply are regulated in such a way, okay, so that they are uniformly distributed over time and space. So uh, apparently, this is very important lesson in here in maximum entropy. Fair is actually mean efficient. Okay, equal, balance. Okay, that mean efficient. Now, if you want to use maximum entropy principle in practice, okay, for any problem, any kind of problem. So what you will do is first you need to find the conflicting situation. Yeah, in our case a while ago, demand and supply, right? But whatever problem that you face next time and you want to optimize, okay, using maximum entropy, okay, first you need to think what is the conflicting situation that you want to optimize. So what is the meaning of conflicting? One variable will increase over x and the other one variable will decrease over x, over the same variable. Okay, and then uh, of course that situation, okay, you need to put into variables, right? And then what you will do is to find the invariance. What is the meaning of invariance? Invariance means if both conflict, yeah, put them together, okay, the best way is actually will become uniform distribution. That is the meaning of invariance. Now, based on that invariance, you create the probability. Okay, and now if with that, now you can use maximum entropy. So why? Because in principle of maximum entropy, you want to balance those invariants, conflicting situation. So you know, if you want to use maximum entropy, you need to find the probability. How do you get probability? You get it from the invariants. What are the invariants? Okay, the invariants are the uh, trade-off between the conflicting variables. Okay, so here are example of conflicting variables. Say you have a network. Okay, in the network you have a flow, you have distance, right? And if you have, for each link in the network, if you have higher flow, that means higher travel time, right? In that link. Okay, so then if you want to go from one origin to destination, okay, uh, we might want to go through a longer route, okay, that actually have lower link flow. You know, oh, that route, if I pass through that route, is small road, not so much traffic. Okay, okay. The smaller flow along the path, okay, will have less total travel time. But the longer route means more distance to travel, right? That means also increase the travel time. So these are an example of conflicting situation, right? So in that case, you know the invariance should be travel time in this case. Why? Because the travel time is along the path, yeah, along the route. So that is a function of flow and the distance. So with that, you can start to find all the path and then the probability of each path. Okay, the travel time of the probability of each path. That is the one that you want to find using maximum entropy. Do you get the idea? Any question? Okay. Remember, in queuing optimization, you have waiting costs, right? And then you have also the server cost. And then you want to trade off between the two to find the number of server. The same thing, right? You have conflicting situation. One is going down, the other one is going up. Okay? So,
Sir, do you perhaps know how max entropy is used in thermodynamics?
a little bit, yes. Why?
Because I'm quite confused on why we use maximum entropy on to solve certain problems when we actually can use like normal optimization, like the one you used before.
There are many ways to optimize, right? So you can use simpler, directly maximize that. The way to do maximum entropy is to find the things that you actually balance things. Okay, so it is the principle that is beautiful rather than the solution, the way to solve itself, right? Okay, the principle is to fairness, to have fairness, to have equality. That is the beautiful part of maximum entropy here. Can you see that? Okay, that's why I'm talking about invariance here. Okay, the solution itself, in fact, there are many algorithms of maximum entropy. I don't even discuss at all, right? I just use solver. Okay, but look, if you have powerful tools like solver, okay, you don't really need to use maximum entropy. Correct, right? So, but why are you going to use maximum entropy? If you want to have to show, okay, that this is actually invariance, okay, it's the process rather than the final goal that is important here. The process of finding the invariance, okay. The invariance is the one that derive your probability, correct? Right. Say you use the directly, yeah? What is that? Maximum of the queuing time a while ago, right? Without maximum entropy. Can you find the invariance? You don't know. Correct. Yeah. You get the result, of course. Even better, right? Than the maximum entropy, right? So, but it is the invariance. It is the uniform thing. It is the fairness. Okay. that is the one that you want to emphasize here. Okay, that is the one that beautiful in this concept of maximum entropy. Using this, you can see, look, is it actually better to have a society? This is the next question, right? Is it actually better to have society that is fair, or actually better to have society that is unfair? Okay, is it better to have organization, okay, company that actually, oh, something like this in economy? Is it better to have a rich and poor, or is it better to have egalitarian society? It is the same. Uniform distribution, not necessarily equal, but almost uniform. So the same with social system, right? So these are the principle behind maximum entropy that is beautiful, that we want to emphasize here. Okay, so again, in summary, okay, maximum entropy serves as unifying theory. Okay, by applying the maximum entropy method, you need to find the invariance, right? So, and you know, this is actually the same as maximum efficiency. This is the one that we want to emphasize in maximum entropy. Okay. The way to solve is not important, isn't it? Okay. You can solve many ways, not just maximum entropy. You can use LP, linear programming. So you can use many different ways. But the beautiful part of maximum entropy is actually the invariance part there, that you can need to highlight. And then from here you can talk about a lot of things, right? Because invariance means fair. Justice. Is justice better than injustice? That's the question. Okay. To answer your question, Joy. Okay, so thank you very much for today. Okay, so next meeting we discuss about Markov chain. Okay, the one I posted, I think is a long time. I will post a new one, but you can read that the one that is already invented.